Okay, I hope everyone sees my screen and that I'm audible. Okay, now you should be able to see my screen. Good morning. I would like to, Amit and I are going to tell you about some advanced features in MPI. In particular, those are mostly part of MPI 3. The MPI 3 standard has been out for a couple of years, but its features are only slowly being adapted, and so we hope to promote that a little. By the way, the MPI 4 standard is pretty close to coming out. Amit and I are in the HPC group of the Texas Advanced Computing Center, and we do a lot of trainings there in MPI and other topics. So this material is also regularly part of our HPC trainings. If you have questions about this, feel free to email us. But during the lecture, feel free to post your questions on Slido, and I hope I'll notice them out of the corner of my eye and will be able to respond to them. Okay, to get started. So the setup of this conference unfortunately does not allow for lab sessions, but I will be doing a couple of code walkthroughs, which in our regular training setup would have been lab sessions. But if you're interested in doing lab sessions, here in the materials, my slides are on the Google Drive of the conference, so you can download them. There are two links. So here is a download link to all the PDFs. There's a full MPI textbook, and the exercises that I'm going to be doing come from an open source repository that has the source of the textbook and of my exercises. I have already downloaded the exercises. So if you download the repository, then you'll find MPI exercises in all your popular languages, C, C++, Fortran, Python even. Okay, so that's about the logistics. So the first link allows you to download the PDFs, and the second one the sources. Okay, advanced features of MPI. So the MPI 3 standard has a number of features, and some of those are purely functionality. So the thinking about the best way to program in MPI, of course, evolves over time, and so features are added, and we'll discuss a couple today. And other features are towards efficiency at exascale, and so we will discuss a couple of those towards the end of my presentation. So even though we have a coffee break in the middle, this presentation is really about 2/3 of me talking about these functionality features, and then in the end, the last 1/3 of the presentation is going to be Amit talking about the performance and tools interface to MPI. Okay, to get some smaller things out of the way, Fortran bindings. So MPI used to be fairly irritating to use from Fortran because the compiler could not do things like see if you had the right number of parameters, and I always used to forget that error parameter at the end, and then the code would compile, but it would crash with completely unintelligible messages. And so as of Fortran 2008, the standard has been cleared up considerably. So MPI 3 demands that you have Fortran 2008, and now you can actually, now the Fortran interface is actually nicer than the C interface. The trailing arrow parameter is finally optional, and MPI data types are no longer integers, so meaning opaque handles. They are type Fortran type objects, and there is a strict type checking on arguments. Can I show those links one more time? Yes, here they are. The links are in the slides, which are on the Google Drive of the conference. So maybe Teja can post the link to where you can find my slides at the conference website. Okay. Okay, so I don't know how you've been using MPI in Fortran. You could do an include of MPI f.h, or you could do use MPI, and they were pretty much the same. Now there is use MPI f08. I see that Amit has posted the link. Thank you very much. If you do use MPI f08, then you get the latest Fortran bindings, which are really nice with interfaces and all that. For the Intel compiler, you need version 18 or newer, and I don't know when GCC started supporting it, but on some TAC machines we still have GCC 7, which is too old for that. GCC 9 works. Okay, the optional error parameter, so like it says, any MPI routine that used to end in an error parameter can now leave that out. It's optional. A bigger difference is that in legacy style, all these MPI objects used to be integers, meaning probably opaque handles. They are now type objects. So to go to edit your codes and make them modern is just a minor amount of editing to catch things like MPI Communicator, MPI Window, etc., and turn them into types. I'll just mention a couple things more. MPI request and MPI status are now also type objects. So what does an MPI wait any call look like? So you have your array of requests. While you're posting your non-blocking sends and receives, you fill in that array of requests. So there is code missing between the second and the third line, and then you do a wait any on however many requests you have. You pass the requests array, it gives you an index, and then yeah, so that in Fortran it all takes care of itself. The allocate call doesn't have to be told what the type is, the wait any. And then you do your test requests index equals MPI request null. Okay, so do remember that MPI request null is all of a sudden also not an integer anymore. So a bunch of these constants have now also turned into Fortran derived type objects. So you may need to update your code for that. A question for the alert student. Is there anything somewhat remarkable about how the index is handled? I'll leave you to ponder that. So MPI Communicator, MPI Request, MPI Data Type, Error Handler Group Info, File, Op, Request, Status, Win. So they've all become objects. What this mostly buys you is type checking. So if you now forget a parameter, then Fortran will complain and say there are not enough parameters or something. The type checking is not entirely perfect, or no, I should say it is perfect, but it's not entirely as informative as you would want. So I've made an artificially broken example. I do a plain MPI send, but somehow I managed to have the count parameter be an 8-byte integer, and MPI send needs a 4-byte integer. And then the compiler will unfortunately not tell me you cannot use an 8-byte int here. It will tell me there is no matching specific subroutine for this generic. Okay, Fortran programmers, you know where this comes from. MPI send is defined through an interface block, and in that interface block are all the different variants of what you can send in MPI. And so this message says that the generic MPI send cannot be resolved into something specific. Unfortunately, yeah, it doesn't quite tell you which parameter is the problem, but you take your code, you match it against the standard, and you'll figure it out. Okay, so this sort of thing used to crash your code in fairly baroque ways, and that is solved now. Okay, so much for the Fortran programmers. Another topic that was solved in MPI 3, and I should say that it gets solved again in MPI 4, is how to treat big data. So I sort of foreshadowed this by having in this example a count parameter that is an integer *8. So maybe you've run into the problem, how do I send really large messages? So some people actually use MPI to send things like executables, and so it's easy to go over over a certain count of bytes, and so the question of big data comes up every once in a while. So MPI 3 has gained a couple of routines that have names like getElements and getExtend, which existed in MPI 1 or 2, but now they have an X for extended at the end. Okay, what is the problem? So in C and in Fortran, you can make a large buffer, meaning more than 2 to the 32 bytes. But the problem is you cannot tell MPI how big that buffer is. See, this parameter has to be an int, and in fact a signed int. So it can only be 2 to the 31, which is 2 billion and a couple. So while you can make a big buffer and MPI doesn't object to sending it, you can actually not tell MPI how big the buffer is. Well, you can be clever about that and solve that as follows. So let's make a contiguous data type that is a little bit under 2 gigabytes. And then you do a send call where you send a bunch of those things. So a bunch of contiguous blocks means one contiguous block, and so now you've sent a really large block of data. So even though the count is larger than what MPI can handle, you've still managed to send this really large message. It is even possible to receive it with the exact same message. So what's the problem? You've sent a large message, you received it, but you cannot query that message. So remember that in a receive call, the count argument is not actually how many elements you're receiving, it's the size of the buffer, which has to be at least as large as what you're receiving. So So you can receive a message, but if you don't know in advance how large it is, you cannot query, because there is, for instance, the routine mpi get count, but that doesn't actually tell you how many floating point numbers there are in the buffer. It tells you how many of these moderately large objects there are. So what you really want to do is mpi get elements, which counts the underlying basic data type. So that was a double here. No, it was a float. So it tells you how many floats there are through this composite message. But mpi get elements returns an int, and so it cannot tell you actually how large the message is. mpi get elements, so this is my own formatting of routines in the standard. Every parameter has one line, and I give the C and the Fortran type. So mpi get elements takes a status. I cannot select it contiguously, apparently. It takes a status argument, and then you query, okay, suppose this message consists of some data type, then how many integers are coming as an output parameter. No, sorry, an integer output parameter of how many elements were in that message. Okay, so that's mpi get elements. So now there is mpi get elements x, and instead of the final parameter being an int count, it is now a mpi count. So that's a new data type. So mpi count is a long int, so it can count more than the 2 to the 31. Okay, and so with mpi get elements x, you can get the count of how many floats were in my message as a mpi count. And so the prototype is exactly the same, except that now the count is no longer an int star, it's an mpi count star. Okay, so after all this complication, and if anyone finds this inelegant, I'm entirely with you. So the MPI committee, after this kind of a stopgap measure in MPI 3, has thought about it some more, and MPI 4, which is about to be ratified, will have 2 variants of every routine. So one with an integer count and with an MPI count. Again, in Fortran this can be done more elegantly than in C, because Fortran has nice polymorphism. You could actually do that in C, but that requires extra language mechanisms. In C++, of course, it would be possible, but in C, to keep it nicely within the language standard, the large count messages will have a _C for count suffix. Okay, so that's how you do large messages in both MPI 3 and upcoming MPI 4. Yeah. So if you've composed non-trivial data types, then sometimes you may have used the routines getExtend or getTrueExtend, and so they tell you precisely how big is what's the distance from the first to the last element in a data type. If you start composing things like MPI type vector, then the extent, so a vector is blocks with gaps, and so the extent tells you the distance from the first to the last block minus the gap at the end. So get extend is occasionally useful. And it returns an integer, hence get extend x. As a sideways remark, MPI for Python uses native Python integers, which are 8 bytes, and so there are no big data routines in MPI for Pi. So this is purely a C and Fortran issue. Okay, I'd like to get to a pretty serious topic, atomic operations. So MPI 2 was the first MPI version that had a one-sided communication, but it suffered from a number of problems. And so one-sided communication is the way out to emulate shared memory in MPI. By the end of my presentation, we'll actually get to actual shared memory in MPI. But as an approximation, one-sided communication can emulate shared memory. So it makes it possible to declare a pool of memory, and processes can put data in there and take data out, regardless of the owner of the pool being aware that it happens. This is in contrast to MPI point-to-point messages, where if someone sends data to another process, the other process has to do a matching receive operation. With one-sided, it becomes put or get, and it's one-sided. The so-called target of the operation is not involved in the sense that it has to do the matching operation. Okay, so what are atomic operations? Race conditions. So once you start doing emulated shared memory, you get all the problems of shared memory, and in particular you get race conditions. So let's just to set the stage, let's look at an example of what you could do with shared memory. So let's say that one process has a table of work descriptors. So you have a bunch of work, and because the items don't take equally much time, you cannot statically distribute them over processes. You want to have a way of dynamically distributing them, and so we do that by storing the table of work descriptors, and a process is going to retrieve one as they are available to do work. So the table, it's actually a stack, and there is a stack pointer that says this is the first unprocessed item. So if a process is available, it reads the stack pointer, gets the work descriptor, starts working on it, and of course decrements the stack pointer. And so this can be dynamic. A process does this only when they're available, and so this dynamic behavior is much harder to do with point-to-point with two-sided operations, because if a process making a dynamic decision, yes, I'm available to do work, it is very hard to have the other side detect that, oh, someone is requesting work from me. Okay, so okay, let's simplify this, and let's say that we boil it down to just the stack pointer. So one process has a counter, and every process reads the counter and decrements it. So we're abstracting away from what actually happens there. Okay, now what's the problem? What is a race condition? A race is who gets there first, and so a race condition is defined as that the outward behavior, the macroscopic behavior of a program depends on timing and synchronization of lower level events. And so the outcome of a program becomes dependent on some low level timing. And race conditions are usually associated with shared memory and shared data. So just to make sure that we're all talking about the same thing, let's say I have two processes and there is a shared integer I, and process 1 is going to add 2 to it, process 2 is adding 3 to it. So what can happen? So scenario 1, both processes read the integer, it's 0, so they both get 0. Now process 1 locally computes I plus 2 is 2, and the other one computes I plus 3 is 3, and now process 1 writes 2, and then for whatever reason process 2 is lagging behind a little, and so it writes 3, and so the outcome is 3. If the lag is slightly different and process 2 does the writing first, then your integer gets updated to 2. Of course, what you really want is that the integer gets updated to 5. One process contributes 2, the other one 3. But that only happens if process 1 does its reading and writing completely before process 2 does it, or the other way around. But basically, scenarios 1 and 2 have the two writes and reads interfere with each other. Okay, this was an abstract example. In MPI, read and write would be MPI get and put. So be careful with interlacing gets and puts. Okay, so what do I have here? This is the beginning of our example. I have a process that owns the counter. And so everyone does a get to find the current counter value, and if my process is available, then a little bit of bookkeeping, but it decrement is -1, counter value gets decremented, and now I do an MPI put of the counter value. Okay, so every process gets the current stack pointer, it decrements it if it decides to use it, and writes the new value in there. Okay, there's any number of things wrong with this example. So the multiple put calls, they conflict with each other. So suppose that this code gets executed by two processes that both say that they are available for work. Then they both write a counter value, they both write the decremented counter value, and without waiting for each other to update it. And so you have multiple puts, and so you get precisely scenario 1 or 2 where you get an incorrect value. This code is actually correct if so let's assume that there is a loop around this. In every iteration of the loop, there is only one process available. So if this code is executed and there is only one process that says that it's available, so in that case there's only one put being done, and so the result is actually correct. I think my audience is on a time delay, so I cannot do interactive questions, but feel free to post in Slido or so if you have an opinion about this. If there's only one writer, can we take out the middle fence? Why was this fence here? Okay, I'll leave you to ponder that. It's a sideways question. Oh yes, and just to test your knowledge of fences, What's wrong with this code? Why? So if you answer the first question, okay, why is the first question? What's the answer to the first question? I can give you that one. If you do a get, you don't actually have the data. There is no coherence between your local variable and the remote result. It only becomes coherent after the fence. So that's what the fence is doing there. So now the second question was, this counter value is only going to be used if you're available. So why not have the fence inside the conditional? Feel free to post the answer. Okay, let's try to improve this. So Mpi put suffers from the problem that maybe multiple processes are writing a value into the process that owns the counter. Well, Mpi2 had a solution to that. So instead of put, you do accumulate. Accumulate is atomic in the sense that now two accumulates actually go on top of each other. You don't know in what sequence they're applied, but that's okay, because until after the fence you're not allowed to ask what's in the counter variable anyway. Okay, so the problem with the multiple puts can be solved with the accumulate, but there is still a problem. The problem is that processes are not getting unique values from the get. So if there are two processes available for doing work, they will both get the same counter value. Okay, so that's obviously wrong. And so what you need is a way to integrate the get and the accumulate. Okay, so, and this was not possible in Mpi2. Not with a great deal of hacking around it, not in any elegant way. So what you want is an atomic operation where the read and update, basically the read and update come together, and it's not possible for another process to get in the middle. So the name for get and set with no one messing with my data is two different routines: fetch and up or get accumulate. The get accumulate has a is very flexible. Fetch and up is a simpler version where you can only write one number into a buffer. The get accumulate is more general. You can write arbitrary data. So what does fetch and up look like? Okay, fetch and up is you specify the buffer that you're writing. You specify where it goes to. You specify what data type it is, and what rank. So what process owns the owns the shared data. You tell it the displacement. Sorry. This is the buffer of what you're adding to the remote window, and this is the read out that you get back. So this is the sort of the put, and this is the get. And so you tell it, okay, who is the target that you're putting and getting to from, and how many bytes into the start of their window area. What is the operation that you're applying to do the reduction? And you need to have the window. Okay, so now what does the operation look like? Let's see, we still have the surrounding fences, but now if you are available, then you apply the decrement. You read out the current counter value. So that's the put part. This is the get part. And then, of course, you tell it that it's an MPI int and what process you apply it to and what the type of reduction is that you do. I did not. So when you do the accumulate, you also had to specify a reduction operator. Okay, so we're pretty far towards a correct atomic operation. So there is a fence and there is a fence, and then you record what the counter value is that you got. Now, why is this if clause not just part of this if clause? Feel free to post the answer in Slido. It again relates to what I said 5 minutes ago about the function of fences. Okay, so this is basically a working code. Let's see. So here's a list of the allowable operators. Most of these you will have seen when you do MPI reduce, but there are a couple that are maybe unusual. So there is replace. So if you do multiple fetch and ops, maybe you don't want to add numbers together, but you simply want to record what is the last one, and so you do an MPI replace. And even stranger, maybe you don't want to make any change at all, and so you can do MPI no op. So that's also a reduction operator. Don't do anything. Okay, so we sort of have a working atomic operation for having a pool of work and retrieving items from it. But so there is a major limitation here. Fences are collective, and so that kind of gets in the way of my statement that I wanted this to be dynamic. So the idea is that a process gets a work descriptor and then goes off and works on it, and then only when it's done with it, it checks back. But having fences means that that kind of interferes with this model. Instead of going off and doing the work, it still has to regularly call this fence. So is there a way to get out of the fences? And yes, that exists, and that is actually not new in MPI 3. That is an MPI 2 mechanism. Let's see, how am I doing for time? So in MPI in MPI one-sided operations, there are two classes of synchronization mechanisms. One is with the fences, which is called active target synchronization. So the target, the process that owns the work pool, is actively involved. And in the code I just showed you, that is apparent by the fact that everyone is doing these fences. Fences are collective. That, by the way, was the answer to the question why you couldn't put the fence inside the conditional. Okay, so fences are collective. Everyone has to call the fence regardless of whether they actually are, in a metaphorical sense, involved in the one-sided communication. So there is a solution to this. Let me immediately go to the second one. So this is the exercise 2, lock fetch shared. So using locks instead of fences is called passive target synchronization. So now the target is no longer involved, and only if a process really wants to do a one-sided operation, then it puts a lock on the remote target, and then it does a transfer, and then it releases the lock again. And so other processes are no longer involved in what's happening here. Okay, let's see. I think this fits on one screen. So, okay. And so the easy way to do this let's see, can I... Yep, I can get this on one screen. So the easy way to do this is if you are the supervisor. So, okay, we have two kind of processes. The supervisor is the one that looks at the counter to see if it went down to 0, and the other one are worker processes. So let's look at the worker processes. So what do? They acquire a lock on the repository. They do a fetch and op, and then they unlock it again. Okay, so now a process only has to do this whenever they are available for work, and otherwise they don't do anything. And here is the supervisor process that does a while loop while there is still work. And what does the supervisor process do? Well, it keeps acquiring a lock on the repository, your code here, so that's where it does the fetch and op, and then it unlocks it again, and it prints what the current readout is. So MPI fetch and op. Let's see if I can. What does fetch and op look like? What am I adding to the repository? Well, actually nothing. So int nothing is 0. So, but what I am interested is reading out the repository. So I have a variable readout. let's see, which is one Mpi int. Oh, sorry, fetch and up is already always 1. So it's an Mpi int. Target rank, I called that one repo. Displacement is 0. Up, and the window. Okay, so now I'm using a fetch and up because it's atomic, but does the supervisor actually do anything with the window? No, it doesn't. It only reads it out. So the operation it does is an Mpi no op. Let's see if I did that. Oh boy, oh boy. It looks like my repository is not entirely up to date. Okay. Okay, so this program, every process reports when they add something to the counter, and the supervisor is occasionally reading it out. At some point it says it's 6, and then the next time it looks at it, it says it's 19, which is, I have 20 processes, so there are 19 non-supervisor processes, and so it notices that the whole work has been done. Okay, so yeah, so this illustrates using fetch and op to do a race-free access to a number. Okay, I'm not going to do the other exercise. So the problem here is now if you have a loop around this, processes are continuously acquiring a lock and releasing it again. And that may be inefficient also because it's exclusive. That means that one process kind of holds up the other ones. So the better solution is to have a block where the whole of the execution is surrounded by a shared lock, which then gets unlocked at the end. And everyone does a shared lock, meaning that now everyone can access the data more or less simultaneously. And because we're still doing fetch and op, it's atomic. But now there is a problem because, again, coherence. Fetch and op does not put the data in your local variable. You have to wait until after the unlock for the data to be there. But now if you surround your whole execution with locks, you don't get the coherence automatically. And so you now need to insert win flush calls. Okay, so this was a deep dive into Mpi one-sided. It is flexible if you have a dynamic workflow, but you have to think about race conditions. So use fetch and whatever, fetch and op. And you have to think about that you may not want to do fences and you want to do passive target synchronization with locks instead. And then if you use the preferred scenario where there is a lock around your complete execution, then you have to do flush operations to make sure that data is coherent, synchronized between the remote target and your local variables. Okay, that's it for atomic operations. Mpi 3 added something to I see no questions on Slido. If they come in, I will answer them. Mpi 3 added non-blocking collectives. So already in Mpi 1 there was send and receive, and then I send, I receive, where a send and a receive are blocking. So you issue a send call, and then you know that when the next line executes, this send has been completely gone through the network. And if you do a receive call, you block, and you know that at the next statement, your receive buffer has the correct result. Collectives are blocking. So if you issue a let's say an all reduce, then your code waits there until the result is actually in place, and there is no way to say, okay, this is my receive buffer for the all reduce. Here's the buffer, please fill it in, and I will check later with, and the checking later is of course the wait call. Okay, but with Mpi 3 you can now do that with collectives. So just like you had Mpi send becomes I send, you have a non-blocking collective where bcast becomes I bcast, and so there are, I don't know, 25 or so, I don't know, 15 different collectives that now all exist in an I variant. So all to all becomes I all to all V becomes I all to all V, etc., etc. So there are a couple of reasons why you could do this, and one is of course overlapping communication computation, but another reason is that it makes your code more resilient to imbalance. Suppose one process is lagging behind a little. Now if you do a blocking operation like an all reduce, then all the other processes are waiting for that one to catch up. Whereas if you only post the request to receive an all reduce, then processes can move on. The operation happens in the background and you check on it later when you need the result. So load imbalance, offset in execution gets evened out a little. Another consideration is pipelining. If you have multiple collectives happening, then you don't have to have one go through the network completely before you can do the next one. You can start pumping them through the network and then checking whether they're done. Okay, so the syntactical difference is extremely minor. So whatever Mpi something was a collective is now becoming I something. You have all the usual arguments, but there is an extra final argument where you get a request, just like with I send and I receive, and then you do some variant of wait for completion. So I bcast is the send buffer, count, data type, root, communicator, and now the extra argument is a output argument of request type. So the overlapping computation communication. So suppose you have two different operations, very different character. You have a matrix vector multiplication, and suppose it's a sparse matrix, so it's almost local. It doesn't involve gathers and all that, for the dense case, and you have an inner product which is not a local operation. It has to involve an all reduce. So then you could post your all reduce, you do whatever is necessary for the matrix vector product, and then you wait for the all reduce request to finish, and then you add everything together. Okay, the usual story about overlapping operations. A more common maybe scenario is where you have multiple reductions. So for instance, if you're running an iterative method, an iterative solution method for linear systems, you need inner products for just getting the mathematics to work, getting your residuals orthogonal. But maybe your stopping test is on something completely different, like an infinity norm. So then you can say, then you do an all reduce for the inner product with a sum reduction, and you do also an all reduce on the z vector, where you, because it's an infinity norm, you do a max. And so now you have two completely different inner products running at the same time, so the data can chase each other through the network. And so these are pipelines through the network, one hopes, and then you wait all until they are both finished. Okay, I'm not going to do this exercise. By the way, if you want to do the exercises, if there is a name in the subject line of the exercise, then that means that, what was this? Proc grid non-block. That means that there is a file with that name that you can do as an exercise. And make files have been set up so that you can, if you type make, it compiles the whole thing for you. That is for people who, after this presentation, are going to be doing the exercises at home. Right, matching. So it is possible to do an MPI send and receive it with an I receive, or do a I send and receive that message with a blocking receive. So you could, for instance, now imagine that you would write a code where if I'm the root, then I really need the result of the reduce, and so I just wait for it. But if I'm not the root, I non-blockingly send my part. Okay, this is illegal. You cannot, every process needs to do either a blocking or a non-blocking collective. As an example of where did I mention that? Yeah, it's again an example of pipelining. Transposing data. Okay, so if you do a multi-dimensional FFT, you take your two-dimensional data set, and every process stores a row of the data set so that it can efficiently do an FFT. But then once you want to do the transform in the other direction, it's extremely inefficient to do that over multiple processes. So you flip the whole grid, and you again do a local FFT in your row. So what does that look like? Flipping the grid means that a column that's stored over processes has to wind up in a row, or conversely that conversely that every process, I cannot select that, every process takes its row and scatters it to columns. So this first row of process 0 becomes a column and it gets scattered over the processes. Okay, so this is kind of a tricky code. What does a transpose look like? A transpose looks like every process needs to scatter its row to the others. So there is a loop over the processes. So everyone scatters, and so every process, so there is multiple scatters, and every scatter has a different route, because first process 0 scatters its row, then 1 scatters its row, then 2 scatters its row. So when a row gets, so I'm assuming that there are 2 arrays, one is called regular and the other one is transpose, and as a result of the scatter, if process iproc is doing the scatter, then everyone gets out of their row of the transpose location iproc. Okay, so that part makes sense. And of course, you get a request out of this. Now, so the receive buffer makes sense. The send buffer, why is that not parameterized with iproc? Well, it's a scatter, so only if you're the root do you have a relevant send buffer, and so I just specify the same send buffer over and over again. Anyway, so I hope that this code kind of makes sense to you. The point here is that I fire off a whole bunch of scatters, and they all have a different route. And so because they have a different route, they, as spelled R-O-O-T, they probably take a different route, R-O-U-T-E, through the network. They have a different route, so they probably have a different spanning tree. And so it is entirely conceivable that these multiple scatters don't collide with each other when they go through the network. And so, in fact, this will have a better performance than doing a sequential bunch of scatters. Okay, so this is a realistic scenario where non-blocking collectives will help performance. Okay, non-blocking barrier. Yes. I've mentioned to people that there is a non-blocking barrier, and they actually laugh out loud. A barrier is everyone stops, and a non-blocking barrier is everyone doesn't stop. So what on earth is this? Well, a barrier is actually not a synchronization in time, but it's a synchronization in state. Reaching a barrier means I've come to a certain state in my program. And so now if you do a non-blocking barrier, then testing on that request means, has everyone reached this state? So, so suppose you have adaptive mesh refinement. You have a large mesh, and only a couple of elements decide to refine their structure, and so they need to tell their neighbors that the message size is changing or whatever, something like that. This is hard to code with. This is hard to code. If almost none of the elements are refining, then does that mean that everyone has to wait for a message? No, nothing is happening. It is so much better if a neighbor could actually detect that it needs to update. So how do you do this? The couple of elements that do actually refine their mess send an update message, and then they post a barrier. And now what everyone does is everyone does a probe for am I getting a request to update? And you test for the barrier. And if you get the barrier, then you know that you didn't need to update. So this is much easier. It's a simple test on a barrier. This mechanism has been known for a long time. So one reference that I found is over 20 years old, and there it's called distributed termination detection. How can you detect a global phenomenon, program terminates, with a local test? So it's exactly the same mechanism. Let me briefly show you. So there is a test. If I need to tell my neighbors something, then I do a send operation. And that code runs to here. And after I'm done sending to my neighbors, I post a barrier. So if I don't update, then I also post a barrier. And now the converse part is where every process does the following. It tests for the barrier. So you get a barrier done flag. And okay, I'm not... this comment stands for if the flag, then jump out of the loop. Otherwise, you do a probe for an incoming message and you absorb that message. Okay, so you're in a loop. You test for the barrier, and if you receive the barrier, it means that there's nothing coming to you. If the barrier is not reached, then you try an iProbe. So this is a simple polling loop. And the alternative to this would be using something like a reduce scatter to detect whether updates need to be done. Okay, I would like to go to a exciting topic in an MPI 3, actual shared memory. So one-sided communication could be used as a simulated shared memory. I was just showing that, and you immediately get all the problems of shared memory, namely race conditions. But one-sided operations are kind of inefficient. There is a lot of synchronization stuff happening under the covers, and some of the MPI designers claim that one-sided can be more efficient, but I've never seen that in practice. Now, the reality is that in modern computers, there is actually a even if you have to do MPI through the network, there is a good amount of shared memory that is shared by a number of cores. The exercise I was just doing was on Frontera, where we have nodes with 56 cores. So there is a good amount of shared memory going on there. And so isn't it possible to actually use that in MPI? And with MPI 3 that is possible. So, okay, first of all, some myths to dispel about MPI versus, say, OpenMP. Okay, MPI processes use network calls, whereas OpenMP use threads, and so therefore OpenMP is more efficient. No, actually. So MPI implementations, of course, detect when two processes are on the same shared memory, and so the network call becomes a copy operation. On the other hand, OpenMP has all this thread management, so it's actually possible for if you're running on shared memory, that MPI is more efficient than OpenMP. No, really, this sort of arguments are not valid. The main problem with MPI on shared memory is data duplication. MPI has the single program multiple data model, so the same code is running on every process, but they have separate data spaces, and so even if all processes really need to have access to the same object, so normally you use MPI to take an object like a finite element mesh and you split it in pieces. But maybe there is something that is really shared because it is the same for every process. In that case, MPI forces you to duplicate it. And so MPI shared memory is a way to get around that. Okay, so what is MPI shared memory? It means that if two processes are actually on the same shared memory, so they are inside the same node, then it is possible to get a totally bare C++ double star pointer. So you can actually get a you don't have to use MPI put and get, you get a real C pointer to another process's memory. Something happened on the chat. Teja, feel free to speak up if that's a question that I need to address. So what do you use MPI shared memory for? So you could use it for doing remote updates like in stencil computations, but I'm not convinced that that is any easier than normal programming. A good use case is if every process needs access to a read-only dataset that is identical. So ray tracing, you have your description of your scene, and that is the same for every process. The thing that is distributed and unique to a process are the rays. So you distribute the rays, but you want your data set to be shared. Okay. Okay, here's a picture of a 4-socket node of our late Ranger cluster. So you see the 4 heat sinks, those are the processors, and they each have a bank of a couple of DIMMs, and so that's what shared memory looks like. The cores in one process can actually access all of this memory on the node. Okay, so what is the mechanism through which MPI can use shared memory? First of all, you know from your communicator manipulation routines that there is MPI COM split. You can split your MPI COM world into sub-communicators. Now there is a new one, MPI COM split type, where you split your communicator based on whether processes are on the same shared memory. In MPI 4, so if you have multiple of these nodes, then you can now split them into the processes that are on a node versus the ones on a different node, etc. In MPI 4, this is going to be extended, and you can actually detect these NUMA domains. But for now, COM split type can only detect shared memory. Okay, You need your one-sided communication calls. So MPI win allocate shared. So that means create your one-sided window in shared memory. And then there is a brand new call shared query, where you actually get a C pointer to the memory in another process. And now instead of doing an MPI put to a process, you do a mem copy or whatever. Okay, com split type is like MPI com split, except that the color becomes the type. MPI com type shared. And so MPI com split type is a routine with a type parameter, and in MPI 3 there is exactly one type parameter. In MPI 4 this is going to be a bit more general. So so you split your communicator, and out of it you get a communicator that contains all the processes that are on your shared memory. And so now you can do com rank and com size.
Hey Victor, I just wanted to let you know really quick, you have about 3 minutes left until break time.
Thank you. 3 minutes till break time, and then the break is 20 minutes, I believe.
Correct.
Okay. Yeah, I'm almost done with this. So we've created the shared communicator. These two examples come from different codes. So node communicator is the shared communicator. So once you've detected your shared memory, you create a window on that shared memory, and then you can do win shared query. So you have a window that lives on the communicator of that node, and out of it you get what's the size, how is the window constructed, and most important, what is the address of that window. And there is no time to do this exercise, but feel free to do that exercise. So from win shared query you get so you tell it, okay, this is the window of shared memory. What process do I want the memory of? And that gives you a pointer to a C pointer to the memory of the other process. Okay, and yeah, so I already sketched this ray tracing, where you have a shared data set, the scene, which would normally live on every process because they have several data spaces, and now you only duplicate it once per node. So it's still not global shared memory, but now with 56 processes on a node, only one has to share this large object. And that can make a considerable difference in your memory usage on the node. And that's it. After the break, I have two more topics, neighborhood collectives, and a little bit about process management. Okay, break.
All right, so it's 10:20 now Mountain Time. We will be back at 10:40 Mountain Time. So we will see you in 20 minutes.
Hello, hello everyone. Welcome back. Welcome back to the uh, Improving Scientific Software workshop, and we're going to return to hear the rest of Victor Eijkhout's tutorial on advanced MPI. Victor?
My video is starting. I'm sharing my desktop. I hope I'm audible. So one of the major topics in MPI 3 that is going to be interesting at large scale is the extension of the concept of a topology. So if you have a very regular application, you may have used MPI's Cartesian topology. So you can tell processes that they are arranged in a multidimensional Cartesian grid, and then you can communicate with a process that is one step in the third dimension away from you or something like that. MPI 1 also had a graph concept, but that was very non-scalable, since every process would needed to specify the whole of the graph. So that latter mechanism has been extended in MPI 3, and so now you can indicate how processes are likely to be communicating along some topology that is specified as a process graph. So we're going to see the routines MPI dist graph, meaning distributed graph create, and MPI dist graph routines related to neighbors, and then new communication routines that you can do on that graph, such as neighbor all gather. So it's an all gather, meaning it's collective, but it's not collective over all processes, it's collective over your neighbors in the graph. So why process topologies? Well, processes don't communicate at random. Quite often you're modeling some 3D physical phenomenon, and the way you distribute it over processes is likely not going to be random, and so the topology of your simulation induces a topology of your processes. For instance, if you have a Cartesian grid, your subdomains will communicate only with a small number of neighbors, and so if subdomains relate to processes, processes communicate with only a couple of neighbors. So wouldn't it be elegant if you could express operations indeed in terms of that topology? So quite often a linear numbering of the variables in your domain and a linear numbering of the processors is a good strategy, but if the two are not entirely a match, then by indicating how processes will be communicating and telling MPI that it is allowed to renumber ranks, it is actually possible to have MPI optimize your application given the communication pattern and given the structure of your cluster. So the graph topology is a way of specifying information from which MPI could deduce how to renumber your processes. Now in MPI 1 there was Cartesian topology and there was a globally specified graph topology. I doubt that too many people used it. In MPI 3, graph topologies are locally specified, and so now all of a sudden it becomes scalable. So to take an example, if you have a 5-point stencil, every process communicates down, right, up, and left. And so what I'm going to argue here is that normally you have to spell it out. You have to do a send and a receive. So you send to your down neighbor, you send to your right neighbor, etc. But by spelling this out, even if you use iSends, you can still get a global behavior that is suboptimal. So suppose you have a 5-point stencil and you spell it out, you communicate in some way around the clock, and so because you have 4 neighbors, it should be possible to do this in 4 steps. If you're a process on the boundary of your grid, you do it in less than 4 steps, but basically everyone has 4 neighbors, so 4 steps should be enough. Okay, so let's say we communicate first down, then to the right, then up, and then to the left. And so I have a 3x3 process grid. Everyone starts communicating. The first 6 processes start by communicating down, and the processes on the last row are blocked from doing anything because they are already involved. So for instance, the last process cannot send up because that channel is already in use. So then in the second step, the bottom row becomes unblocked, and so all the processes that did their communication down are now communicating to the right. But now there is a problem with the middle communicator, the middle process. It has already done its down communication, but it tries to send to the right, but the right communicator, the right process, is already communicating with the one below it. The one above it is also involved in something, and the one to the left is. So there is one process that is blocked from anything, so it misses one turn, and so the global communication, which should have been done in 4 steps, will take at least 5 steps. Okay, so this is one of these cases where spelling out the communication pattern gives a overall execution time that is suboptimal. So just like you use a collective call like reduce instead of spelling it out as sends and receives, you want to be able to use some collective like call to spell out this behavior where you say, okay, I communicate with all my neighbors, and you don't spell it out in what sequence. So that's where the neighborhood collective comes in. So it's called an MPI neighbor all gather. It's really a local gather. So the combination of gather and neighbor describes that it is a gather, meaning you collect from a set of processes, but it's not the global communicator. It is a neighbor subset. So again, using iSends and iReceives is just as limiting as spelling out how to do a collective. So you want to just say, okay, these are all the processes I communicate with, and now let's leave it to the MPI layer to orchestrate the actual data movement. Another reason for neighborhood collectives is that if you do iSends and iReceives, the buffer has to go as a whole, whereas if you spell it out as a collective, then MPI can use pipelining and spanning trees and optimize the transfer just like it did with traditional collectives. So this can potentially be much more efficient. Okay, what does a routine look like for creating this neighbor graph? MPI dist graph create. There are two routines, dist graph create and dist graph create adjacent. So you start with your old communicator, MPI com world or whatever. Number of sources. So how many processes are going to be sending? Okay, now this is a distributed graph. It's a distributed graph. So every process describes a distributed bit of information. So n sources, that's the name that's used in the standard, but I don't like it. What it actually says is how many processes are being described here. So usually you say n sources is 1, and then the array of sources is your own number, so your com rank. Okay, so with dist graph create, you can say, okay, I call this, and if I am process 0, I'm describing everyone. Or you can, so that is very centralized. Or you can say, okay, every process describes one node in the graph, and it describes only itself. Okay, so how many nodes are you describing, and what are the degrees of these nodes, and then an array of destinations. So the array of destinations has a length of the sums of all the degrees. You can have a weighted graph if you want to indicate that certain communications are more important than others, and if it doesn't matter, then you specify MPI unweighted. It is possible to pass information with MPI info. You may have seen the MPI info object in MPI IO, where you give it hints about the file system, or in one-sided communication where you tell it something about the structure of the shared memory and that sort of thing. In this case, I'm not quite sure what you would specify, so MPI info null is good enough for me. Int reorder, so you want to give MPI the option to shuffle the processes to bring ones that communicate with each other often closer together. And out of it comes a distributed graph. Now this is kind of an interesting object. So in this picture, suppose you're one of the purple nodes and you describe, okay, that is one node, it has degree 4, and these are the 4 neighbors. Now what do you think that the distributed graph communicator is going to be? Is that going to be a subcommunicator of just those 5 nodes? Actually, it is not. It has the same nodes as your original communicator, but it is annotated with the graph properties. Okay, so that may be a source of confusion. This graph is not it's not a subcommunicator describing the neighborhood. It is a communicator describing all the processes in the original graph with extra information. Okay, and now you do a neighbor all gather. So it's an all gather, meaning information is gathered into a buffer and everyone receives that. Well, everyone receives the information from their neighbor. So it is not quite the same as a regular all gather. In a regular all gather, everyone gets a copy of the same information. In this case, everyone gets a gather from their neighborhood. So it is all in the sense that everyone is gathering, but not in the sense that everyone gets a identical receive buffer. Okay, so everyone contributes their send buffer count data type. So that's the in this picture, all the orange ones contribute their bit that is going in the ghost region of the purple one. And the purple one declares a receive buffer count data type. Okay, so there's only a single count parameter. And so this is the case where everyone contributes the same amount of information to the ghost region, which is of course not the case if you have an irregular application. And so there is an all gather, MPI neighbor all gather V for the general case. Now, so after the all gather, you have a receive buffer and it contains all the information. But unlike with the regular all gather, where your buffer contains information from that it gathered from 0, then gathered from 1, from 2, 3, etc., etc., in this case, the information is not in the normal rank order. So you need 2 more routines. You have your gathered buffer, but you don't know precisely what's in it. So first of all, you need to ask, okay, how many neighbors do I have? Why do you need that? Well, this is neighbors in the sense of who you receive from. What was I looking at? All right. I didn't emphasize that here, but when you create the graph, you're actually specifying out degrees. I have no idea what the rationalization behind it is, but with this call, you specify how many processes you are sending to. Whereas if you do a gather, you're more interested in how many did I receive from, and so that's where you do the neighbors count. And then there is the routine MPI dist graph neighbors, which actually tells you what the numbers are in order in which they are present in your buffer. Okay. Yeah, dist graph neighbors. It's a routine that is surprisingly longer than you might expect that it is. There is an exercise, but I don't think I will have enough time for that. So if you take my full-length MPI course, then one of the recurring exercises is suppose every process is sending its data to its neighbor. And so one of the intriguing aspect of that exercise is that this should really happen in time order 1, but for instance, if you use blocking sends and receives, it has a running time proportional in number of processors. So if you take my MPI course, you get to do this with blocking sends, with send receive, with non-blocking calls, with one-sided communication, and then finally you get to do this as a neighborhood graph exercise. So this is the exercise: get data from your neighbor. And I don't think I have enough time to actually do this exercise. Let's see if I can. So okay, let's see. So I'm creating a graph, and what I want to do is receive from the left. So that means that because I have to specify it as outgoing, the number of sources is 1, except if what do I call it? nproc. No. If my process number is the number of processes minus 1, then I am not sending anything to the right, so n sources is 0. Sources is an array of who am I specifying the graph for. So oops, that's only the local number. Destinations. Who am I sending it to? That is my graph plus my number plus 1 int degrees. I hope I get this array syntax correct. These days I'm completely C++, so I've forgotten how to declare arrays. I hope this is correct. And the degrees is 1. Actually, let's do it like this. If I'm on the right, then the degree is 0. Otherwise, I'm sending to someone. Okay, and then I execute that thing. So the neighborhood all gather. Let's see if it works if I declare only one neighbor, and then let's leave it at this. Oh, weights is undefined. Okay, let's see what happens if I run this. Okay, so what's happening? Every process is reporting what it is gathering. So every process is sending its own process number, and so 2 is it has a buffer of 2 elements, and the second, and because there is only one process communicating, it does get the one. So which one is the last one? 19. Oh yes. So the last process. So the last process. At the last process, I didn't specify anything, because there's no outgoing data, but still it gathered it correctly. So I'm not entirely sure why in this design the graph you specify is the dual of the graph that is being used for the gathering, but that's it. Okay. Oops, I didn't mean to do that. The final topic that I will spend about 5 minutes on is okay, I won't go into intercommunicators. They are tricky, but they happen if you do MPI process management. So you always thought that MPI COM world was the largest group of processes. Well, there's actually a universe, an MPI universe. Namely, it is possible to dynamically spawn processes, and for that you have to indicate how much space there is beyond your COM world. So MPI is getting close to 30 years old. It dates to 1992 or so, but of course there were distributed memory libraries before MPI. One of them being PVM, Parallel Virtual Machine. And one of the things PVM could do that MPI 1 couldn't was dynamically create new processes. And so for that reason, PVM actually stuck around for quite a while MPI existed. And then in MPI 2, MPI gained the capacity for doing process management. Okay, so how does this work? You use MPI attribute get to get the size of the universe, which is your world plus what is outside it, and you create new processes. And because MPI COM world is fixed, new processes live in their own COM world, and you need something called an intercommunicator to communicate between the original COM world and the new COM world. So MPI COM world is now called an intra-communicator, and the thing that bridges it is called an intercommunicator. Okay, so how does this work? You need to have a way of saying this many processes are started and this much space is there. So the standard suggests that MPI exec start 4 processes, but there is a universe space of 8. At TAC we have IB run, which is MPI exec but tuned for the InfiniBand fabric, and you use an environment option, my MPI run options, and you say universe is 8, and then you spawn 4, and now your process can get an attribute. So it can query what is the size of the universe. Ta-dam. And now you say, for instance, okay, the number of workers. So having a manager worker model, the manager says, okay, I take my universe minus my world size, and that is how many workers I can spawn. A character string, what is the name of my worker program, and then I say com spawn worker program, and you can give it arguments and you tell it how many workers. And so these new workers are going to be in a com world by themselves. Okay, And so these worker programs start up as if they got started from the command line, and so they can do com rank and size, asking, okay, how many buddies do I have? And that does not include the manager that started them up, but they can ask, okay, do I have a parent? Do I have someone that spawned me? And if you do that on the parent, you get MPI-COM null. If you do it on a worker, it will tell you, yes, there is a parent, and this will give you the intercommunicator so that you can communicate with your parents. And that's as much as I wanted to say about this. So, this mechanism is actually an interesting one. Attack, we have a user who has a program that he cannot alter, and so that program runs in a COM world, but he really wants to make that program more parallel, and so he uses the COM spawn mechanism to start multiple of these programs. Because you can add argv arguments to the spawn call, you can actually dynamically spawn the worker program with arguments. And so this is like a dynamic task model by spawning MPI programs. Okay, that's about as much as I wanted to say about MPI. So what have we done? Fortran Bindings, something about big data, atomic one-sided, non-blocking collectives, actual shared memory on node, something about process topologies, and a little bit about process management. Okay, that's about as advanced as you can get in MPI 3. Except if you listen to my colleague Amit, who is going to tell you about the tools and the profiler interface.